SSCS daily chapter. So this talk is challenges of high-speed wireline communication circuits and systems. So we have us with us from Intel Bangalore. So Tapas is an industry semiconductor in with 32 years of experience in various design and managerial capabilities for analog and mixed signal IPs and products spanning over wireline communication PHYs, data converters, power management, clocking, thermal sensor, IOs, etc. Tapas started his career in CDAC, Pune, India, and worked in ST Microelectronics and Synopsys before joining Intel Bangalore. He holds a Master of Technology degree from IIT Kanpur and Bachelor of Engineering, Electronics and Telecommunication from Bengal Engineering College. Tapas has 12 granted and 2 filed patents, 6 publications in international conferences, and he has delivered talks in various forums. He is a senior member of IEEE and Solid State Circuits Society. So Tapas, a long career, right? And we really want to hear, your talk on this. Thank you very much. Go ahead, please.
Okay, let me share my screen. Just 1 second. Let me know if I'm audible enough and my slide is visible.
Yes, your slide is visible and you are audible.
Okay, thank you.
Yes.
First of all, I'm honored to be here, and thank you, SSCS Delhi chapter, to invite me to give a talk in this forum. Very good morning, good afternoon, and good evening to my friends in Europe, India, and Far East, respectively. Today, I'm going to talk about a topic which is challenges of high-speed wireline communication between ICs and associated circuits and system. Legal disclaimer from my company, though there is no confidential in it, most of the contents are from published domain, IEEE conferences and publications and journals. We mentioned those citations in the relevant slides. I will not specifically talk about it. The author names and the publication citation is mentioned in every slide. As we move on to the agenda, before we talk about the agenda, I would like to mention one fact that I believe today we have a very wide audience, starting from students in electronics engineering, senior students doing masters and PhD, young professionals, and experienced professionals too. So during the talk, I'll be touching upon sometimes on the very basics. During that time, at least the experienced professionals should bear with me so that everybody is at least more or less on the same page. And on some of the slides, we will be pacing up because those are the topics that cannot be covered in this short talk. They are very vast topics, and mostly they will be towards the end when we are going to talk about the current trends and future directions. Coming back to agenda, I will introduce the topic as necessary. Then we'll talk about some challenges, starting from a very simple one to the complex ones and their solutions. And as I mentioned before, we'll talk about the current and future trends a bit. As a part of introduction, we have to introduce what are the wireline communications. As we know they are the cabled connection between computers and peripherals, connection on the backplane board, then communication using USB, or some of them which we don't see because they're encased within the equipment, like communication between the camera and the processor, the display and the processor within the mobile, or between dies in a multi-chip module. Before getting into the technicalities of it, I would like to talk about just a few minutes on the commercial aspect of it. In 2022, IP Nest has published one study of the value of the IPs that was sold the previous year, 2021. The values means the ones that were sold as well as the ones they are in-house developed. And no wonder the largest value of the IPs is CPU due to ARM and a lot of other CPUs too. The second largest one is the interface, which is almost 1/4 of the entire pie. Interface is nothing but the wireline communication IPs. And there are several other pies, several other IPs occupying the pie. So the young professionals and students who are planning to make a career in wireline communication, I can assure that you will not repent it at all. Let's move on to what is there inside the wireline communication. To establish the need for it, let's look at the history a bit. In the last century, we had the ICs, the dies like this one, classically. The core is in the center where you have the CPUs, the analog and all other digital logic, and wire bonded IOs on the periphery. One of the wire bonded driver, means transmitter, is shown here, which is nothing but an inverting amplifier, which is driving the signal to the outside world. Similar way, another inverter or Schmitt trigger, which takes the signal inside. With the core shrinking following Moore's law, and the speed was increasing, the data crunching speed was increasing within the core, the demand on the IO, the demand on transferring the data to other ICs were increasing. The demand in terms of pins times megahertz were increasing in earlier years, almost 50% year over year. Whereas the bonding technology and higher voltage IO switching were not going as fast as the demand rising. They were going almost half of the speed. Hence, there was a need for running all these IOs at much higher speed to cope up with the demand. We try to run the standard IOs or some variants of it, like SSTL, HSTL, at much higher frequency, but it was prohibitive due to ringing noise on the inductance on the bonding wire, huge power consumption due to CV square F, reflections, they are mostly deterrent. During that time, a low voltage differential signaling transceiver came into our rescue. It's around mid-90s where National Semiconductor, if I recollect, made this low voltage differential signaling transceiver or LVDS transceivers very popular. The circuit is very simple with a current source and sink and an H-bridge driver or the switches, which was driving current on a differential pad onto a resistor from top to bottom to create a positive differential voltage, or from bottom to top to create a negative differential voltage. If we have an amplitude of one end of it determined by a delta V, usually they are few hundreds of millivolt. That's why they are low voltage. Then the differential signaling is around 2 times delta V, and differential peak to peak swing turns out to be 4 times delta V. In terms of binary, if we want to send a 0, we send from bottom to top, which effectively is a negative differential voltage. We tell them as we name them as -1. And if you're sending a +1 binary, if you're sending a binary 1, we send it from top to bottom to create a positive differential voltage to create a +1. It happens on a nearly stable common mode voltage, so noise effect goes away. Because of the low swing, the swing can be made much faster. In those days, few hundred megahertz or megabits per second can be transmitted. We'll introduce this term later. On the receiver side, we have a standard differential amplifier. These are basics to convert it to a CMOS level. Or we use a strong arm latch, which is almost like a sense amplifier of a memory, which are clocked. So with this particular technology, people were able to send data, which are, say, a few hundred megabits per second, means 1 megabit means 1 million bits per second. 100 million bits means 100 Mbps, and so on and so forth. Whenever this speed was increasing, the data rate related frequency and its wavelength, whenever this wavelength becomes comparable to the baud trace or cable trace of transmission of data, the transmission line effects come into picture, so was reflection. And it's a simple challenge. So simple bookish solution were also proposed to have a calibrated impedance within the die, sometimes at the transmitter end, sometimes at the receiver end, and even for higher data rate for a longer cable length on both ends. So that solves the simple problem. By that time, the first baby step was taken to transmit data from one IC to the another IC. This is the start of wireline communication. In this simple structure, we transmit the parallel data from CPU or internal logic, serialize them, send it over a couple of LVDS transmitters, which are terminated, goes over the cable or baud trace. On the receiver side, we do have a receiver, like we mentioned in the last slide. Along with that, we send a clock also. We used to send a clock also. Usually it is divided by 2 to reduce the number of toggles, and data is supposed to be clocked on the receiver end using positive edge as well as the negative edge of the clock. Few fundamentals here. We already talked about the naming and numbering convention, 0 as -1, 1 as +1. 1 bit period of the data transmission is called 1 unit interval. If we take a random data folded over unit interval, we get an eye diagram. And usually data rates, as we mentioned before, are in terms of 1 by UI Mbps or GBps, and like that. And the Nyquist frequency, the highest Nyquist frequency associated with this kind of data transmission is 1 by 2 UI, which effectively means if you are sending 100 Mbps data, the Nyquist frequency will be 50 megahertz. If you're sending 1 Gbps of data, the Nyquist frequency will be 500 megahertz, so on and so forth. With this kind of techniques, at the receiver end, every bit which was sent over these differential lines are registered on the receiver side by either positive edge of the clock as well as on the negative edge of the clock, meeting the setup and hold time. It is almost like a standard standard synchronous design, digital synchronous design. That's why this method of communication between two ICs are called source synchronous system or clock forwarded system, because we forward the clock. In this methodology, we were able to send several hundreds of Mbps of data per data line from one IC to another IC. As we have seen, there are more and more data demands come up. We became even more greedy, so started sending data at a GBps, 1 Gbps to 2 Gbps rate over a board trace, which is not long, 5 to 7 inches, which can be of the size of a mobile phone. So whenever we try to do that, beyond 1 Gbps of data rate over 5 to 7 inches of trace, we face a challenge which is not so simple. That's why I strike it off. It becomes very difficult to maintain the skew between data and the clocks. Ideally, the clock should be in the middle of the data to maintain the setup and hold and properly retrieve the data on the receiver end. But because of this speed, where the bit period becomes 1 nanosecond for a 1 Gbps link, or 500 picosecond for a 2 Gbps link, maintaining skew over the clock, maintaining skew over 5 to 7 inches for a clock and data becomes difficult. Often, the clock edges align with the edge of the data instead, and wrong data were clocked in. For this kind of challenge, it was mitigated by a solution called Deskewing. In the Deskewing, we retrieve the clock only using a clock buffer. Then we pass it through a DLL or delay lock loop. Delay lock loop is nothing but a series of voltage controlled delay lines, which maintains a relation between multiple copies of the clock at a fixed phase relation. In this case, it is 30 degrees between them. And the delay line is controlled by a simple type 1 proportional control system to control the voltage, to fill the entire delay line by a single clock period or a half a clock period in this particular case. So we create multiple copies of the clock at a fixed phase difference. This DLL is followed by a phase interpolator, which is nothing but series of multiplexers which selects 2 consecutive phases from the DLL, followed by a phase mixer, which mixes an early phase with the next late phase with different strengths that is controlled by the digital world. And once we are able to mix with the different strength of an early phase to the late phase, we are able to place the clock edge very finely between two coarse phases of the clock. So this entire circuitry gives a possibility of finely placing the clock phases anywhere within the clock period. That gives us a possibility of putting the edges back on the middle of the data. And this is only the possibility of finally controlling the phase. But how do we move the clock phase back onto the middle of the data is the job of a control circuit called CDR. It's a vast topic. So we get a clock, so it's not a true sense CDR, but loosely we can say it recovers the phase of the clock, and we will talk about the CDR later. In the next slide, we will introduce this CDR topic. CDR itself is a servo control loop. Like in any other servo control loop, you need to find out the error in the system. What is the error in the system? Ideally, we like the clock phase to be in the middle of the data period or bit period. However, if we are placing a clock in the middle, or if it moves to the left or right, just by looking at it, we know that there's not much of error information we can retrieve from here. Hence, we need to sample the bit period at least 2 times. One at the intended middle of the bit period, and the second on the intended edge of the bit period. by another fixed relation clock phase. So that means the data phase of the clock and the age phase of the clock have a fixed relation between them. So all of them will move together. Once we are able to sample the age of the data period, slight movement to the left or slight movement to the right, we will be able to find out the error. And this error is found out by a circuitry here, which is called a phase detector. There are several kinds of phase detectors present. The one that we have used here is called the Alexander or bang-bang phase detector. It consists of a couple of flip-flops and a couple of XOR gates. To understand the operation of this phase detector, or Alexander phase detector, we can refer to the waveform here. If the clock age, the age which is supposed to be aligned to the data age, the clock is late, that means the age is towards the right, we have the next data bit sample and the current age sample same, but opposite of the data bit of the which is current. If the clock is early, exactly the opposite thing happen, which means the age of the age sample becomes same as the data sample, but becomes opposite or different from the next data bit. If there is no data that there is a transition, if the data remains same consecutively, they are 1 or they are -1. In that case, there is no error that can be retrieved. So with this information, whether the clock is late or the clock is early, or we do not have any information, we take this data as a +1, this error information as a +1, no information, which is 0, or a -1 as early, late, and no information. We dump these errors onto a proportional controller with an integrator. The digital integrator is nothing but an accumulator. And we create set of digital codes. This digital code goes to the digital to phase converter, which is nothing but the phase selector from the DLL and the phase interpolator, as we mentioned before. So we select, looking at this code, we select 2 consecutive phases to be interpolated by the strength of the rest of the digital code and place the clock finely over a period, and then again compare with the phase detector. That's how we are able to control and bring the edge phase to the edge of 2 bit periods. And because we have a fixed relation with the age sample, age clock to the data clock will be brought to the middle of the data bit, and we are able to retrieve the data properly on the receiver side. There are several kinds of phase detectors. Alexander is not the only one, like Hogg's phase detector, Mueller, Qureshi. We are not going to talk about them because they by themselves are a topic. Now, before we move on to the next challenge, I mean, in the previous slide, we recovered the phase of the clock. And before we get on to the next phase, where to understand the next complex challenge, we will spare a little bit on the fundamentals of jitter. Jitter is nothing but a jitter of a clock or jitter of a data is nothing but the deviation of the real clock or real data age from its ideal position. And if we find out the difference in time from its ideal position and plot it across the time, we get different kind of periodic pattern, or sometimes a totally random pattern which cannot be divided into any kind of period or derived into any kind of period. So with this kind of extractions, we can categorize jitter into 2 main types. One is deterministic jitter, which can actually be simulated by transient simulators. Deterministic jitters can be sinusoidal, like this deviation will be perfectly like a sinusoid of different frequency, of course, or data-dependent jitter, which can be intersymbol interference. We will introduce this topic later on, or can be a duty cycle distortion of the clock, or a crosstalk induced bounded uncorrelated jitter. The other category is a random jitter. Usually their variation is like a Gaussian variation, and they are never bounded. Deterministic jitter is always bounded. We can identify the maximum deviation that may happen, but the statistical form of jitter, which is a random jitter, can never be bounded to a maximum value. But of course, we can predict by a probability. If we take the probability density function of each type of jitter, which are usually present in the system simultaneously, and we convolve them together, we get a very complex probability density function of the jitter. And once this jitter superimposes on the data edges, and the eye diagram edges become quite fuzzy. And the center of the eye is still assumed here to be open so that at least one clock phase, as we discussed before, can retrieve the data. But we do have a random jitter, which has unbounded edge. So often this unbounded edge will go towards the middle of the eye, and we start getting an error in the retrieved data. Because it is a statistical phenomena for the unbounded jitter, we do have a concept called bit error rate, which means one error in 1 million transmitted bit, that becomes 10 to the power minus 6 bit error rate, or 1 billion transmitted bit, that means 10 to the power minus 9 bit error rate, or one error in 1 trillion transmitted bit. Transmitted bits means 10 to the power minus 12 bit error rate. So with this concept of jitter, let's get back to our source synchronous system, where we know that we are sending a clock and a data with a definitive skew between them. They are not edge aligned. Ideally, they are supposed to be, the clock is supposed to be in the middle of the data. And this deliberate skew, and then there is a jitter on the clock as well as data. Then there is a frequency or the time period of that jitter that is also present. Now, depending on the relation of the time period of the jitter, not the data time period, it's the jitter time period of the time period of the jitter on the clock and data. If they maintain an integer relation between them, then at the receiver end, the relative delay between the clock and data, or relative jitter between the clock and data, becomes negligible or becomes null. But for other jitter frequencies, this Q, which is fixed, may not have an integer relation between them. If they don't have an integer relation between them, often they add up. So the input jitter on the clock sometimes double up. To solve this problem, people started employing PLL on the clock to filter out the high frequency jitter from the clock and live with the data jitter only. On top of that, if you're sending a clock, high frequency clock, over a lossy channel, that will come to this topic a bit later. But for the completion's sake, let's look at this topic once, at least now. If we are sending a high frequency clock over a lossy channel due to some kind of an intersymbol interference, the clock jitter gets amplified. Here also, we need to employ some kind of a PLL on the receiver side to filter it out as much as possible. So you can see we are sending a clock. We are wasting silicon area, we are wasting package and board area to transmit a clock, but the clock itself is amplifying the jitter, which is not to our liking. On top of that, we are bound to use a PLL to clean up this clock on the receiver side. That opens up another possibility of data transmission. Why not? We get rid of transmitting the clock altogether, and we embed some of the edges inside the data pattern. So by encoding, say 8-bit, 10-bit, or different kind of encoding or data scrambling, we ensure minimum number of edges that happens within a random pattern of data. That is called clock embedded communication. In this clock embedded communication, because the clock is not being transmitted, we need some mechanism to extract the clock from the incoming data. And by the way, this type of communication is called clock embedded system or plesiochronous system. Coming back here, on the receiver side, we do need some kind of a circuit which extracts the clock from the data. And this is called a true CDR, where not only it extracts the phase, it also extracts the clock from the data stream. There are, and this extracted clock finally are used in the sampler or flip-flop kind of a data slicer to clock in the right data into the receiver. There are three kinds of CDRs that is present in this world. The first type is a blind oversampling CDR. Second one is a pure analog PLL based CDR. And the third type is a digital DCO based or phase rotator based CDR. We will take quick glimpse at each of them. The first type, as we mentioned, blind oversampling CDR. As the name suggests, we do not have any information about the edges of the data, and we oversample them by multiple phases or much higher frequency. Once we sample them and we get enough number of samples per bit, we do an XOR between consecutive samples. And whenever there is a change in data, that means the data boundary occurs, we identify them by the XOR output. XOR will be 1. Whenever there is no change in data, XOR output will be 0. By that, we find out the exact location of the edges of the data stream. And from there, we move away to pick up a sample, which is supposed to be a good data. There are other methods of extracting the data from oversampled CDR using quasi-linear phase error and proportional integral controller, but we will not get into it. It will take a long time to discuss. This type of CDRs, because we need more number of samples, we need much higher frequency of the clock or many more number of phases of the clock. Naturally, we would be needing more power and more area. Moreover, this kind of system is not really manageable beyond 6 to 8 Gbps of that order. That's why people moved on to the other type of CDRs. However, for a sideband channel in today's wireline communication, as well as a low frequency management bit transmissions, the oversampling techniques are still in use. So let's move on to the next type of CDR, what we call classical analog PLL based CDR. In this type, we have a PLL circuit. It's a charge pump based simple PLL using VCO, loop filter, charge pump. Only difference is at the input, instead of a phase frequency detector of a classical PLL, we use a phase detector. And this phase detector can be the same phase detector as we discussed before, like bang bang phase detector or Alexander phase detector. And the VCO is as classical, either ring oscillator based or LC tank based, depending on the phase noise. This PLL gives us a transfer function, which is a type 2 system with its parameters, the natural frequency and damping factor, where we do have the phase detector gain, which also depends on the incoming transition density of the data as well as the noise. It is actually a low pass filter, and because the VCO frequency can be slightly off from the exact input frequency or input data rate, we need to track not only the position, we need to track the slight frequency difference between the VCO and the incoming stream. If we have a slight frequency difference, we do have a phase ramp. So effectively, not only we need to find the position error and correct it, we need to track the ramp error on the incoming data stream. That's why we need a type 2 system as directed by the standard control theory. The key process indicator for this kind of CDR, or for that matter, any kind of CDR, is the jitter tracking, which effectively means we have a data stream which is coming in, which is jittered. The CDR is extracting the data, extracting the clock from this data stream, but CDR is a low pass function here. So some of the jitter frequencies, CDR is able to extract properly and track it properly and pass it on to the clock of the receiver so that the data and the retrieved clock do not have any differential jitter between them. But at a higher frequency, the error will become predominant. Hence, this tracking function is a high pass function. Low pass frequencies can be totally tracked, no problem, but the error will be predominant at higher frequency jitter. To know how robust, how resilient the CDR is, we need to measure it actually on silicon, but there is no direct way you can measure this resilience. So there is an alternative way of measuring the CDR in the silicon, where on a perfect pseudo-random data pattern, there are some fixed frequency jitter is impinged on, fixed frequency and fixed amplitude jitter. The frequency and the amplitude of the jitter are varied in the testing, as well as the amplitude of the jitter is varied on the testing. And then from the received data pattern, it is found out what are the number of errors, whether any error has occurred. With different jitter frequency and different jitter amplitude, we do have some region where error is allowed, which means the CDR is a pass. But in some region, if there is any error, we call the CDR has failed. And the boundary between them is usually determined or usually specified in most of the wireline specifications, which can actually be derived from this jitter tracking function by the simple equation, which is input jitter frequency and amplitude normalized to unit interval of the bit period. The usable part of the I, which is phi m, normalized to the bit period over a jitter tracking function. So if we get a proper measurement here, we can find out the CDR's bandwidth from this kind of jitter tolerance curve, as well as its tracking resilience on silicon. However, the analog type of CDRs have most of the components, or rather all the components which are analog in nature, like resistor, capacitors, they vary a lot over the process, temperature, and voltage. And also, it takes longer time to port from one technology to another technology. That's how the latest type of CDR came into play, which is called a digital CDR. The digital CDR has a PLL, which is locked to a frequency pretty close to the incoming data stream, pretty close, but not exactly same. And multiple phases out of this PLL are fed into the blue box, which is actually our digital CDR. These multiple phases are phase rotated using the same technique of phase selection and phase interpolation. Finally placed phase of the clock is used to clock in the input data, and the error is detected by a phase detector, which is same as the bang bang or Alexander phase detector. The error information is passed on to a finite state machine, which in turn controls the phase rotation component. So if we look at the diagram of this digital phase detector, we do have a bang bang phase detector whose error values are decimated to some extent because the digital finite state machine operates at much lower frequency. So we need to reduce the number of errors fed into the digital world. And then the FSM actually consists of a proportional path and integral path, and then followed by a phase integrator like a proportional integral control loop. That finally controls the phase rotation, what here we call it phase to digital or digital to phase converter. There are equivalents between the analog CDR and the digital CDR. The phase detector is exactly same. The proportional path is quite similar to the resistance of the loop filter of the PLL based CDR, as well as the integral part is quite similar to the capacitor of the analog CDR. And phase integrator plus the digital to phase converter, which is nothing but a phase rotator, put together forms analogy of the VCO. The only thing that is not present in analog is a decimation filter. Whenever we make a Z transform of this circuit, we do get a transfer function of the digital CDR. If we plot them, we do get a CDR transfer function, jitter tolerance transfer function. Now, because we can control this proportional path gain, integral path gain in much more finer way than we can control these capacitors, resistors, etc., we can have a finer control of the CDR bandwidth, CDR peaking, or jitter tolerance tracking. With this, we come to the final stage of one very critical parameter or one very critical phenomena of the wireline communication, where the input data streams phase as well as exact frequency is retrieved on the receiver side to retrieve the data properly with minimum number of error. Maybe I can continue to the next challenge, which is much more complex challenge. Whenever we transmit data over a baud trace or a cable, they're usually copper cable or copper baud traces of different quality. Due to the skin effect, dielectric loss, etc. of those transmission lines are lossy in nature. And often the 3 dB frequency of those lossy transmission line, lossy means they are low pass filter. The 3 dB frequency of those lossy low pass filter transmission lines are much smaller compared to the data rate that we need to pump in through those kind of media, means baud trace or cable. So now if we transmit much higher frequency random data over a lossy channel way above the 3 dB cut-in frequency, a single pulse gets distorted, smeared over, to spread over to the next bit period, to next bit period, as well as to previous bit periods. And whenever this spread pulse are superimposed, because there are a continuous stream of data that is coming in, we do get a waveform like the one at the bottom. And you can see the waveforms struggle to reach the decision threshold. If we make an eye diagram out of this kind of traces, we do get a totally closed eye. So there is nothing in the middle to clock in properly the data. How do we solve this problem? One option is, or rather only one option, is to introduce some kind of a high pass filter in the system. If we put a high pass filter, and if we can control the high pass nature of that filter, which cancels the low pass nature of the board trace or the cable, then we are done. We are able to equalize this loss, which effectively means if we have consecutive ones or zeros, that is the DC component or near DC component of the data, we suppress them greatly. And whenever there is a data transition, single pulse or clock-like patterns, we amplify them. By this method, we equalize the data stream so that the eye diagram, the eye opens up, and from that eye diagram, we are able to retrieve the data properly. One of this high pass filter is quite commonly used in the wireline system. It's called continuous time linear equalizer, or CTLE in brief. There's nothing but a differential amplifier on the receiver that is used in the receiver with source degeneration resistor and capacitor. At low frequency, the capacitor is open, the gain is greatly reduced by RD by RS, roughly around RD by RS. At high frequency, the capacitor shorts the source degeneration resistor, and we get a higher gain like GMRD. We do have another parasitic pole anyway that is coming from the parasitic pole of the load circuit. So this system has 1 0 due to this source degeneration resistor and capacitor. And of course, the same guy gives another pole also. Here in this case, we call it pole 2. And there is a load pole, which is a pole 1. This pole 2 and pole 1 positions can be changed by design if we can control the parasitic capacitance. Ideally, we should be targeting whatever is called pole 1 as a load pole here to be after the source degeneration pole, which is named as a pole 2. It doesn't matter. These are all design techniques that people do use. The key process indicator for this kind of CTLE is the zero position and the boost of the CTLE. Boost means what is the gain difference of the high frequency at near the Nyquist frequency of the data stream versus the DC. And this value, the zero position and the boost, can be changed by changing the resistance and capacitance. There are several variants of this kind of CTLE available in literature. So we just gave a glimpse of it only. In this kind of circuit, high pass circuit, we do have a problem of high frequency noise amplification. That actually creates a major problem. So we cannot really have too much of a boost in CTLE. So we resort to another type of equalization, which is called feed-forward equalization, or in brief called FFE. Usually they are used in the transmitter, but that doesn't stop anyone to use it in the receiver too. To understand its function, let's look at the red pulse, only the red pulse, ignore the blue pulse for the time being. When this red pulse at the transmitter end passes through the lossy channel, as we mentioned before, the pulse shape gets distorted and smeared all over. And we do get this pulse interfere onto the next bit period, onto next to next bit period, as well as on the previous bit period. This interference are called inter-symbol interference, and the amount of interference is called post cursors if they happen to the later bits, and precursor if they happen to the previous bits. Now, let's concentrate on the blue waveform, where the single red pulse is pre-distorted in such a way that we do have some opposite pulses of definitive amplitude before the pulse as well as after the pulse. So that means by single pulse, we convert that one into 3 pulses in this particular example, of course, and we use opposite pulses of certain amplitude so that this inter-symbol interference caused by the main pulse, which is called the cursor pulse, gets nullified. We do have a reduction in amplitude, but inter-symbol interference get cancelled out. This kind of techniques are actually the finite impulse response filter. You can say it is finite impulse response in mixed signal domain, where we have we generate that by delaying the pulse by 1 unit or 2 unit interval, and then multiply the pulse by some positive coefficient, some negative coefficients, add them up to form this kind of a blue pulse. And once we send the data stream, we do get a pre-distorted transmitted pulse like that. Just for a circuit level example, we take one example of 2 tap, means 1 cursor pulse and 1 post cursor pulse. We use, this is a circuit example. We use 2 LVDS transmitter connected in opposite fashion so that they subtract each other. And the strength of these LVDS transmitters are controlled by their tail currents, and the ratio of their tail currents to the total current is the coefficient that we call as the coefficient of equalization. Just by looking at the circuit, you can realize that if we are sending continuous ones or continuous zeros, means continuous minus ones, the copy of the pulse here as well as the copy of the pulse after a bit period remain same. So their strength gets subtracted here, and we get a level W0 minus W1. The moment there is a change in data bit, we do have the opposite signal comes over here, and instead of subtraction, the addition happens on the line, and we do get a level which is W0 plus W1, either for on the plus side or as well as for the minus side. This is how the 2-tap feed-forward equalizer is realized in circuit, and it can be extended to multiple taps. We'll not go into the equations for the sake of time. Just to understand on the frequency domain or body domain, the red one is a channel loss, which is a low pass filter, and we just saw that DC is suppressed by W0 minus W1, and high frequency component or AC is boosted by W0 plus W1. So the feed forward equalizer acts like a high pass filter to give overall channel flat response, provided we can control these 2 coefficients. However, in this method too, The positive point is we can even use it for precursor cancellation too, as we have shown in the last slide. But noise amplification do happen here also. It is very difficult to use it in the receiver because we need to sample the analog diminished voltage and do all the multiplication and addition operations. Because we suppress greatly the DC amplitude, the I diagram, the final I diagram after the feed-forward equalization diminishes. So these are the negative points. Then we look at a third category of equalization, which is called decision feedback equalization. Here, and it is used only in the receiver. Here, after the cursor decision is taken, that means whether the cursor is +1 or -1, that decision is taken. We know from a pulse response during signal integrity simulation, we know the amount of ISI. If it's a plus pulse, it is a plus ISI. If it is a -1 pulse, which is in exactly the opposite direction, it's a mirror image, we get a minus intersymbol interference of the post cursor, intersymbol interference of the second post cursor, so on, so forth. The diagram is shown here where we take a decision like a strong arm latch. We delay that decision. We multiply by the amount of ISI and we subtract from the incoming stream so that the ISI gets cancelled. And a close eye opens up using this decision feedback equalizer. The right bottom picture is an example of a summer or subtractor, you can say. It's a CML type current mode summer, which is shown here. And the slicer or data decision are taken as a standard strong arm latch that we have introduced during LVDS slide. Now, there is a major problem the moment we introduce this DFE. As we mentioned that we use a strong arm latch as a slicer, the strong arm latch means it has to integrate and regenerate a very small analog input. So it takes its sweet little time to recover the data from a very small, say 10, 20, 30, or 40 millivolt input data stream, which is highly diminished due to low pass frequency response at the input. On top of that, there are some settling time for the summer, it's the analog settling time. And for any kind of latch, we need a setup time. So putting all this required time together, the slicer's own time, the summer time, and the setup time, all this thing has to be lower than 1 unit interval. That means this loop time has to be less than 1 unit interval. Imagine you are sending a data at 10 gigabits per second. By this time, we became even more greedy and started sending way beyond 1 Gbps data. Here we start talking about 10 plus Gbps data where 1 unit interval is only 100 picosecond. And keeping this loop time within 100 picosecond in several technologies, I'm not talking about the very cutting edge technologies, for several technologies, it is difficult. So the solution of this difficult challenge is to pre-compute both the possibilities of the decision. Had the decision been +1 or had the decision been -1, we pre-compute them. And finally, when the next decision is made, we pick up the right data through a multiplexer. This is called loop unrolling or speculative DFE. In the waveform, it is shown in a way that the dashed line here is the possible input data stream. For example's sake, consider this one is going towards a +1, and we don't know yet what happened to the previous bit. We pre-compute, or we add a plus H1 coefficient, which is the coefficient of DFE, and a minus H1 coefficient from the incoming data stream. It happens either here or it happens in this case also. Now, if the previous bit is a -1, then we select the green line, and you can see the green line is above the decision threshold. That's how DFE opens up the eye. If my previous bit is a +1, then we select the blue one, where you can see it goes close to the decision threshold, but not really that much. It goes close to the expected eye level. That's how we control the low frequency components to open up the eye to a controlled voltage level. Usually only the first tap is loop unrolled, because the first tap suffers from this large delay in the slicer. The other taps can be directly fed back onto the summer. So this picture shows a multi-tap DFE with first tap loop unrolled. Note here, the positive point is because you already have taken a decision, there is no noise amplification. The decision has already been taken. However, we cannot cancel a precursor. We can only cancel the postcursor, because we can take a decision. We can do the correction only when the decision is taken. That's why it's called decision feedback equalization. The next point is, how do we determine this coefficient? Let's take an example of DFE coefficient. How do you determine that? If the media is not changing, that means I have two ICs placed on a fixed board. The board trace is fixed. We can do a signal integrity simulation. We find out the pulse response of the board. We know the ISI amount, and we subtract, as we have been talking about. However, that is not a very optimum. The reason being, over process voltage and temperature, this pulse response do change a bit. To make the situation even worse, if you have a plug-and-play system, like PCI card being plugged in or plugged out, like an HDMI cable, you change the HDMI cable of your TV, or a new USB is connected, USB device is connected on the USB port. So these are called all plug-and-play situation. Under that kind of condition, it is almost impossible to know a priori what exactly is the coefficient needed, what exactly is the pulse response of this kind of system. So the only way we can solve this problem is to adapt the system. How do we adapt? We determine an expected eye level. Say, maybe the slicer can resolve a plus and minus 50 millivolt or plus and minus 100 millivolt. So we determine two green levels as plus and minus 100 millivolt for argument's sake. And we introduce, apart from the slicer, which is a strong arm latch here itself, we introduce another strong arm latch whose decision threshold is shifted up or shifted down depending on the level that we are comparing. So this additional slicer, we call it a monitor slicer. So it monitors the eye level. So if any trace, incoming trace, is not able to cross the eye level, the monitor slicer is able to give an error, which is negative error, because it has not crossed the eye level. It can happen also on the negative side. If the trace has not crossed the eye level expected, it will give a negative error. But for a coefficient, if we are using a coefficient which is much bigger, then the eye level can go the trace can go above the expected eye level, and the monitor slicer will give a positive error. So we just look at the error sign, which is a +1 or a -1 from this error slicer, as well as the data slicer has the decision threshold, in this case differential 0, and taking up the decisions, assuming that we are able to take up the decision properly. This particular waveform clearly explains what we mean. Assume the previous bit is negative -1, and the current bit is a +1, and we are using a coefficient which is overcompensating or over equalizing the system. That means the wave trace will jump very fast and well above the eye level. So we get a positive error. Similarly, if the bit is not changing from the previous one, both of them are +1, the current bit as well as the previous bit, both of them are +1, and we overcompensate it. What happens? Overcompensation means we subtract too much and we get a negative error. So with this kind of phenomena, we devise an algorithm called sign LMS, where the sign of the error multiplied with the sign of the previous bit, then looking at the multiplication of these two signs, which is nothing but an XNOR function, we find out whether this multiplication output, the product, is a +1 or -1. Knowing that, if it's a +1, we adjust the current coefficient, say H1 coefficient, by a small amount. If it's negative, we subtract the H1 coefficient by a small amount to the next iteration. This is how the H1 coefficient in the iteration, one after another, the iteration of the adaptation, by one after another, we achieve a value which is pretty close to the level. This is called sign LMS algorithm. And this example shows in terms of DFE. And this particular equation corrects the first post-cursor DFE coefficient, which is H1 in this case. What happens to the other taps? Because we can have second post-cursor, third post-cursor, mth post-cursor. If we need to correct the mth post-cursor coefficient, we correlate and multiply the current error with the sign of the current error. We multiply with the sign of the mth previous symbol that we received. And we use the same multiplication kind of table and adjust mth coefficient, mth post-cursor coefficient in iterative process to achieve the correct value. Okay, so we talked about so far the overall system. If we already talked about the LVDS transmitter. We talked about this, the CDR. We talked about feed-forward equalization, CTLE, decision feedback equalization, adaptation, CDR, everything. So if we put all those ideas together, we get more or less a classical wireline system. On the transmitter side, on the left, we do have a wide parallel data, encoded data, which gets serialized. Then it is passed through a transmitter side feed-forward equalizer. The serial data is passed through a LVDS transmitter whose output impedance is calibrated, passes through a lossy transmission line. Again, it gets terminated to avoid the reflection. Then it goes through a CTLE of limited boost. Then it goes through a decision feedback equalization or DFE with multiple taps. We do have the sine LMS engine to determine the coefficients H1 to Hn. And then we have the sample data. Here it is shown only one sample. Ideally, for a normal CDR, we need at least two samples, as we have discussed before. We pick up those two samples, pass it through a CDR. Then the CDR aligns the clock to sample properly. We retrieve the serial data, convert them to parallel data, pass it on to the next level in the receiver. This is a classical overall picture of wireline communication in plesiosynchronous system. With this classical architecture, we are able to, there are few variants, of course, available. There is no doubt about it. We are able to handle the data rate 6 to 8 Gbps or below, up to a data rate 32 Gbps and above, and in few cases 50 plus Gbps also, by using this classical method. So what does it mean? We have invented everything and our job is done. And do you think all the problems solved? Anyway, looks like we will take the questions at the end. So as we mentioned that, do we think all the problems solved? That means we as engineer and designers, we don't have much to do. We twiddle our thumb or lose our job. Luckily, that's not the case. If we look at statistics again, which was taken in 2019, per internet minute, which means in 60 seconds, there are 694 hours of Netflix, our equivalent of data, downloaded through Netflix. 3.8 million searches happen on Google. Facebook, 1 million logins happen in 1 minute. 18 million texts are sent. And even 1.4 million swipes on Tinder, my God. So each of these operations every minute all over the world causes some data to transfer from one server to another server, one tower of the server to another tower, one rack to another rack, as well as one IC to another IC. So we are back in business due to growing data transfer demand. As per ISSCC's wireline trends in 2022, which means this year, it has been tracked over past few years too. It has been seen that the demand as well as the data rate which is handled every 3 to 4 years, it is doubling. And designers are able to handle that. In 2022, there are 224 Gbps of data rate communication, which was demonstrated in ISSCC by Intel. So let's look at, for such a huge data rate, how do we handle such huge data rate and what are the challenges behind it? Let's look at a situation. We will talk mostly at 56 Gbps in these following examples. That can be extended to higher Gbps rates, because 56 Gbps is at the starting end of this very high speed data rates. So this 56 Gbps data rate has to go through the long reach backplane, which is usually 1 meter or 40-inch backplane in the server. This backplane or this trace on the PCB causes a huge loss. If you're trying to send data at 56 Gbps, non-return to zero, that means binary communication +1 and -1. we do get a loss of 60 dB. Effectively means if you are sending data at 1 volt differential, we would receive 1 millivolt differential here at 56 Gbps NRZ. 56 Gbps means the Nyquist rate is 28 gigahertz. That's where we need to look at the loss. Along with this loss, even if you think that by CTLE, FFE, DFE, with all those kinds of equalization techniques, you're somehow able to retrieve the data. But the major phenomena is there is a crosstalk also, which is of almost of the same level and makes it very difficult to segregate between them. So it is not really viable to send data at NRZ mode at that speed. Hence, we move away from NRZ mode. We start sending 2 bits at a time using 4 levels, which is called PAM4 communication system. The moment we send 2 bits at a time, we can increase the bit period, or rather the symbol period. Now it's no longer bit because it's a symbol consisting of 2 bits. So the moment we are able to encode 2 bits into 4 levels using PAM4, our Nyquist rate comes down by 1 octave. 28 gigahertz becomes 14 gigahertz. And we have a sizable gap from the crosstalk. And the gain is also a lot less, which is 30 dB, which means 100 times. Now, what is the inflection point for where we start sending NRZ and where we start sending PAM4? If we look at the inflection point here, just look at the levels. If we are limited to send only 1 volt differential, and if we want to encode in that voltage space 4 levels, we reduce our signal to noise ratio or level to level difference by 1/3, right? 1/3 means a 9 dB loss in signal to noise ratio. So if a loss in the channel, when we are sending only clock-like pattern, there are other impairments that we are not going to talk about at this moment. If you're sending only a clock-like pattern, and if you're sending over a lossy channel where over a decade of frequency, the insertion loss is much more than 9 dB, then it makes sense to move towards PAM4 instead of sticking to NRZ. In this particular case, over 40-inch backplane in the server, the loss improved from minus 60 dB to minus 31 dB, almost 30 dB improvement, way beyond 9 dB. So it makes sense to move from NRZ level of communication to PAM4 level of communication. Now we will speed up because it's a big topic and we will not talk about each component here. In the interest of time, or maybe some other day, we will talk about the PAM4 separately. We will introduce different components of the PAM4 wireline architecture in a single slide. Looking at the transmitter, we definitely need to transmit 4 levels, right? Because it's PAM4. If you recollect the first FFE slide that we mentioned, there we need to pre-distort every level by a certain amount. If we need to do the FFE on the transmitter, and definitely in this lossy channel, we do need to do the FFE, that introduces many more pre-distorted levels than just 4 levels. So the transmitter has to be a multi-bit digital to analog converter or DAC. Usually a current mode DAC is used because they are very much well equipped for high speed operation, though there are voltage mode DACs also present. Then on the receiver side, after the channel, I think terminations and etc. we are not going to talk about here. The terminations are not only resistor, usually they have a combination of resistor and inductor to avoid the capacitive loss in the channel or in the ESD, in the impedance itself. But we'll not talk about that. Just remember that we need to introduce inductor in the terminations too. We do have the classical CTLE and VGA, of course. We have to introduce inductors on the load also, load resistance. We have to introduce inductors too to boost up the bandwidth, because now we are talking about a very high speed. If we just talk about 56 Gbps PAM4, which means 28 gigabaud per second, right? So the Nyquist frequency will be 14 gigahertz. So this is how all these analog signal processing has to handle for a 56 Gbps. And naturally, if we move to 112 Gbps or 224 Gbps, this Nyquist frequency also has to jump by the same order of magnitude or same multiplication factor. After the analog components, we do not use a slicer any longer. We do use the ADC, because not only the transmitter with FFE created multiple levels, the loss in the channel also cause multiple levels that we need to sample at the right place. And these multiple levels need to be sampled by an ADC, which is very, very high speed. What is the sampling rate of the ADC? Again, we take an example of 56 Gbps. What is the baud rate? It is 28 gigabaud per second. So we need to sample at least once per symbol period. So it means 28 gigasamples per second. If we have 112 Gbps data rate, the ADC has to sample at 56 gigasamples per second. So it's a very high-speed ADC. Usually, they are achieved by asynchronous successive approximation ADC. Use each successive approximation ADC, which operates at 1 gigasamples or between 1 to 2 gigasamples per second. We use multiple of them, time interleave them to achieve such a high speed. So you can say this ADC is a time interleaved successive asynchronous successive approximation SAR ADCs combination. So each ADC, SAR ADCs combination, and each ADC sample one bit period once or one symbol period once, and then dumps the data. Usually, these ADCs are 5 to 7 bit, between 5 to 7 bits. So that means 2 to the power 5 to 2 to the power 7 number of slices that is possible to represent any analog signal. We can represent that one in digital world by 5 to 7 bits. These 5 to 7 bits per bit are parallelized, dumped onto a relatively lower speed DSP. What does this DSP do? At the heart of it, we do have, again, the equalizer, because CTLE is not able to open the eye fully because we cannot really employ so much of boosting. So we need to use some other technique of feed-forward equalization, other techniques of equalization. As we mentioned before, instead of analog way, now we have a digital way of feed-forward equalization happening in the DSP at the receiver side. Here, the multiplication of the coefficient, addition, everything happens in the digital domain. After the feed-forward equalization, we do have the DFE also, loop unrolling also in the digital domain. And finally, after this equalization, we do get multiple levels of data. Using digital comparator, that means using a very simple digital threshold, and to see whether a level is above that digital threshold or below that digital threshold, we can identify 4 distinct levels and decode them to 2 bits that we already transmitted. On top of that, even the monitor slicer can also be implemented in the digital domain to find out whether the error due to a particular FFE and DFE coefficients is over equalizing or under equalizing that level. We find out the error just by using another digital comparator. And this error in the monitor slicer, as well as the bits retrieved so, are passed on to the adaptation logic, exactly the same way we adapted using sin LMS, as well as we use a CDR, which is a baud rate CDR, where we need to use the sample data. Baud rate CDR means we sample only 1 times per symbol period, and we use the sampled data as well as the error data to be passed on to the CDR for a baud rate CDR that we did not discuss in detail, but maybe in some other future, some other time in future, we will talk about them. So effectively, if you look at, this is the overall system using a PAM4 wireline communication at 56, usually at 56 Gbps and above, 56, 112, 225, and 224, and this kind of levels. We do use ADC followed by DSP way of data retrieval and transmission. So it's fairly complicated, isn't it? What does it do, all this complicated system? Effectively, it transmits in the system, in the server, from one switch IC to another switch IC. They can be in the same rack, they can be in different racks, different cards, etc. And they pass through the backplane, which is the same long reach backplane, lossy backplane that we talked about. Using PAM4, if you're sending a 56 Gbps, we get the Nyquist rate at 14 gigahertz. We do get somewhere around 31 plus or 30 plus dB loss in this channel. Do we really need to struggle so much, waste so much of power, with so much of energy on it? The server guys came to the rescue by reducing this backplane distance, reducing it to the half. So the communication between one switch IC to another switch IC, switch IC means data switching IC. Now the distance between the switch ICs are half of it, which is a medium reach. But we cannot effectively keep on reducing this length using copper only, because first point is we cannot pack too many cards together because it generates too much of a heat also. And then there is a mechanical limit of how much low you can go in. So people started looking at alternatives. And as an alternative, we got optics. So where from the switched IC, we transmit over a short distance, say around 15 centimeter in the server, to an electrical to optical converter IC, or you can call it optics, which in turn feeds onto the fiber optic channel. Now further work goes on, and here the loss is quite less because we moved the optics pretty close to the switch IC. Now at 14 gigahertz, we do have around 10 dB loss. Then we move even further, which means move the optics even closer and take care of the rest of the distance that data has to travel by optical fiber. So as we are moving closer and closer, different loss of the channels are coming down from long reach to medium reach to very short reach to extra short reach. And finally, people are talking about moving the optics inside the same package as the switch die. So it's called co-package optics, where the loss is extremely low. So we probably don't need a PAM4 there. We move on to the NRZ mode of communication for same 56 Gbps. But yes, PAM4 will be needed the moment we move towards higher and higher data rate. So in the server, the future direction is covering most of the longer distance by optics and increasing the data rate of the switching at much higher and higher speed. As we mentioned, 112 Gbps is almost getting commissioned and 224 Gbps will happen in future. So this is where the server and the high data rates are moving. What happens to the rest of the world? If we just look at a glimpse of a little bit of a history too, from the day MOS was invented and CMOS was invented, the planar MOS was shrinking following Moore's law and following Dennard's scaling law, till the point around 2005 where leakage became so dominant that shrinking it any further was not making sense. So industry started looking at alternative MOS structures like SOI and FinFETs. But this kind of MOSes are difficult to make. So the Moore scaling slowed down a bit. Though there is no stopping, the new kind of MOS has been announced by a couple of foundries, which is called gate-all-around technology, including Intel in this year only, 2022. But as we say that this kind of MOSes are very expensive to make, very difficult to make, and getting yield is also difficult on that. Hence, industry started moving towards disaggregation around 2015-16 timeframe. Though multi-chip module was there even before, but the usage picked up during this time frame. Disaggregation means you can have dies, the design dies from different technologies packed in the same 3D IC and the same package by packed horizontally or vertically. And that's where the era of 3D IC coming into picture. And once we move into the 3D IC, we need more advancement in the packaging by different packaging techniques, different connectivity techniques. And Moore's law started continuing and will continue in 3D domain, even though the IRDS has given the scaling limit only up to 2034. Maybe they will extend or maybe they will not. But Moore's law and packing and everything will continue even beyond when we move towards 3D IC. So what goes inside 3D IC? If we look at a package, classical ones with which means almost a multi-chip module, where the dies are stacked horizontally and they are interconnected through the package substrate. It's almost like a PCB within the package. Or the dies are packaged partially vertically, partially horizontally, and the dies are interconnected through a silicon interposer where you have the metal layers to have much finer connectivity between them. So this kind of packaging is called 2.5D integration, or a pure 3D integration where the SoC, the processor, the ASIC, the RAMs, the IOs, everybody are stacking on top of each other, and they're getting connected by different technology of feed through silicon via. Today, most of the packages or the advanced packages are a mixture of all three of them. The moment you put the dies together, you need to, because you disaggregated the entire system into multiple dies, you need to communicate quite heavily between the dies. And that is done by a die-to-die interconnect. Usually the die-to-die interconnect has multiple channels. Each channel has one common lane with PLL, with different references, etc., followed by 40 to 80 single-ended transmitter in one direction and single-ended receiver in the other direction, 40 to 80 of them clubbed together. And one clock is also sent in the transmitter direction, as well as one clock is sent back the receiver direction. So they are mostly the source synchronous. You can see we are going back to the first level. However, instead of differential, now we have single-ended transmissions. Along with this channel, we do have few spare lanes. The reason behind, the connections are extremely fine and feeble. So often in the package, you do get some manufacturing defects or it breaks. So there are spare lanes also packed within, and there are logic which takes care of this broken lanes by alternate spare lanes. On the transmitter side, we again use a Deskewing loop, as we discussed before, and a duty cycle corrector to align the clock phase of the SoC, with the clock phase of the phi transmitter, so that we do not have to use any FIFO in the transmitter side. That reduces the latency. And on the receiver side, we do have a clock, and we know that the skew can be bad between the clock and the received data. So we do need a Deskewing loop, as we discussed initially, and a DCC for a proper DDR communication to align the clock on the receiver side. So what are the main challenges here? Because we need to transmit over a large number of lanes in single-ended manner, we do get into the crosstalk issues. So we need to put proper signal integrity analysis, put proper number of grounds and supplies in between, and transmit the data to keep the crosstalk to a manageable range. Just for your information, usually this data communication per line, not lane, per line is approximately 6, and people are trying even 6 to 8 Gbps, and people are also trying to go towards 16 Gbps per line. And it will keep on increasing, as we know, as the technique improves, this data rate will improve, and so on and so forth. The second challenge is the power delivery, because you need to send the power from the board through the ball, through the package, through the small, through silicon via or very fine lines onto a particular die. So it is highly inductive and resistive layer to provide the proper power to the dies. So these are the two main challenges that we face. What are the key figure of merit or process indicator? First of all is you have a huge number of wireline communication between dies. So energy efficiency is the key parameter. Energy efficiency is usually measured in terms of picojoule per bit, which in a way you can measure milliwatt of power that you need to consume to transmit 1 gigabits of data to be transmitted. Milliwatt per Gbps is exactly same as picojoule per bit. And the trending figure of merit is 5 picojoule per bit and below. Of course, you broke a system into multiple dies, so you cannot really have too much of latency between them. So we need to reduce the latency between the communication, die-to-die communication. That's why we use even Deskewing and DCC in the transmitter loop too, to avoid FIFO too. And the latencies are hovering around 5 nanosecond time frame. The third figure of merit is the bandwidth. As we mentioned, on every direction, if you're sending, say, 8 Gbps NRZ communication, then we need to have this entire file that will take some space in the die edge, right? How many such transmitters and how many such receivers we can pack together so that the overall throughput through the edge of the die is very high. So that is called the bandwidth per short line. The trending is usually greater than 1 terabits per second per millimeter of die edge. And usually these trending numbers I picked up from Shengao, which was published in this year's CICP conference. For a vertical die-to-die communication, we do have a much finer through silicon vias, which connects between lower die to upper die. So area matters a lot. So what is the bandwidth density? That means the number of vertical lines that move, each of them carrying, say, 8 or 10 or 16 Gbps of data per unit millimeter square. So that becomes a bandwidth per area, which is hovering around 10 terabits per second per millimeter square, as per the latest published data. So where do we stand? With the advantage, or we're taking the advantage of the emerging technologies, which are called CoWoS, nothing but die-to-die connection, very fine through silicon vias of TSMC, Foveros, EMIBs means embedded multi-die bridge. All these techniques are allowing us to connect between dies vertically as well as connect between dies horizontally with a much more packing density. We are improving the bond pitch from 25 micrometer to less, even 10 micrometer or less. You can see that. With the packaging interconnect getting compact, vertical stacking is gaining popularity with multiple dies getting vertically stacked together. With that, we are reducing the channel length between die to die from 2 millimeter to 100 micrometer. If we look at the trend that was published in the same paper, where x-axis is the die-to-die communication length in millimeter. So it starts from around 2 millimeter, 3 millimeter to around 100 to less than 100 millimeter, less than 100 micrometer. And on the y-axis, the figure of merit means bandwidth per energy density. Bandwidth density means terabits per millimeter square, and energy efficiency is picojoule per bit. The trend line is with the reduction in bond pitch, which is reducing from 40 micrometer, 25 micrometer, 20 micrometer, and even lower. The trend is improving the bandwidth density over energy efficiency. And finally, with a very small very small channel to be covered between two dies, we revert back to sending just an inverter IO plus the flip-flop, almost like a die-to-die interconnect, as if it's seamless, and each interconnect line over few Gbps. So finally, we come back to simple inverter and flip-flop with few Gbps with a very high packing density given by these latest technologies. We start calling them light IOs. So we are back to the basic IOs. Does it mean that everything is over? No, not really. Be ready. There will be more and more die-to-die connectivities. More dies will be packed within the same package. So the length between one die to another die for the communication will increase. The connections will become thinner and thinner, so the loss will increase. So we will be back again with all the techniques that we discussed, one after another. We will do the deskewing. We will use the CDR of different techniques. We will again use the equalization. Then we will use NRZ mode to PAM4 mode, or maybe even PAM16 mode, and so on and so forth. The only difference will be you have to achieve all of them with much lower power. With that, I conclude my talk. Hopefully, I could give an overall glimpse, or rather, I would say that it's a tip of the iceberg only. This topic is much, much wide, much, much deeper. So at least I'm able to give some overall picture of the wireline communication, the basics, and current and coming trends. Now, I stop here and your journey begins, those who are working on it and those who will be working on it. I'm open to the questions now. I think we do have 15 minutes. Sanjay, I leave it to you how you handle the questions to be passed on. First of all, are you there?
Yes. Yes, Tapas,
Okay.
I'm here, very much here. And yeah, first of all, I would really like to thank you for such an enlightening talk about the wireline communication. As you mentioned, this is really, really a wide and a deep topic, and too much uh, scope of innovation going down the line, as you mentioned, and too much has already happened. Yeah, the journey is yet to begin on the new front, on the multi stack dies, as you mentioned. So thank you once again for such a nice talk. And yeah, as you mentioned, the floor is open for any questions from any of the audience, please. You can open speak up the question.
I see Kaushik, Dr. Kaushik Saha has a question. Yeah, go ahead.
Right, Mr. Nandy, my name is Kaushik Saha. I am with the Electrical Engineering Department of IIT Delhi. For all, a lot of the methods that you have described in this very illuminating talk are very closely related to network physical layer communications in wireline LAN or wide area network communications, right?
Exactly.
Now,
these are all PHY communications. These are called PHYs actually. Physical
yes, PHY
interfaces.
communication. So physical area layer communication. Now, in physical layer in telecom systems, we also have the concept of error correction, right? With the spot error correction using Viterbi codes, and then block codes for burst error corrections, etc. Have you come across any literature? Have you given any thought to use of such methods for die to die or chip to chip or rack to rack communication, as you've described, because
Absolutely.
they can lead to very high, fairly substantial coding gains in SNR.
Absolutely, you are right. If I may show this graph again, um, usually in PAM4, if we look at the energy communication um, up to 32 Gbps, the bit error rate allowed is 10e minus 12 range. That means one bit error allowed per 1 trillion bits. But the moment you move to PAM4, because signal to noise ratio is less, plus there are errors, there are quantization errors in the DAC, in the ADC, everywhere. The raw physical interface is not able to cope up with that kind of demand on bit error rate. Usually, by specification, it is 10e minus 5, 10e minus 4 level. People do achieve 10e minus 6 in this kind of wireline interface using ADC and DAC and DSP. What we didn't talk about are the forward error correction that is employed just above in the link layer of this PHY, where in the forward error correction on the transmitter, and of course the error detection and correction in the receiver side improves this bit error rate to, if I may recollect, 10e minus 15 level. Yes, you are right. This kind of techniques are used. There's a block encoding. Forward error corrections are widely used.
There's a forward error correction encoding is there.
Yeah.
Another question,
right.
Another thing that was bothering me is, the serial parallel and parallel serial interfaces really have to be clocked at much higher frequencies than the processor frequency. Say the processor is going at 3.5 gigahertz, but you're clocking out your data on the serial line at 14 gigahertz, right? With the 14 gigahertz clock. So, are such clocks used now? I mean, a 14 gigahertz clock and all that?
Yes, actually, the serializer and deserializer on the other side, they didn't go in detail because it's a simple, and naturally we couldn't go too much in detail in this 2-hour talk. The serializer is actually a staged serializer. Unfortunately, I do not have a picture where, say, a 64-bit wide data comes from the digital. That 64 wide data first serialized into 16-bit. That means 1/4 with 4 times higher frequency than the digital world. And then that 16-bit is further serialized using higher and higher frequency stage by stage with multiplexer serializers. Similarly, the same thing happens on the receiver side to deserialize or parallelize the serial data into parallel data. It happens in stages. So you have a clock of 14 gigahertz on the PHY. That 14 gigahertz you divide by 2, divide by 2 again, divide by 2 again, like that, up to divide by 16. You use almost 1 point something gigahertz clock to serialize the oncoming data from 64-bit wide to 16-bit wide. And then you use 2 gigahertz to make 16-bit to 8-bit data, and so on and so forth. And you do the same thing on the receiver side. So it is done in stages.
So there exists a 14 gigahertz clock.
There exists a 14 gigahertz clock in the PHY and its divided parts in the PHY. So PHY takes care of it.
All right. So the 14 gigahertz clock itself is a design challenge.
Oh, yes, itself. Absolutely. They are mostly the LC tank oscillators. And even the clock distribution, people spend months together to manage the distribution of this clock.
Wonderful. Thank you. We should talk more about this offline sometime. Thank you, Mr.
Absolutely.
Malik.
Just do give me a call.
Yeah. Any more questions?
I believe, is there any question on the chat window? Maybe we can check that.
So sorry. This is Wei from NXP. I have one question. Firstly, thank you for the great presentation. I have a question. Is there any method to verify the equalization function in production ATE test? As you know, sometimes we just use the internal loopback to cover the SerDes function in production test. But as you know, generally the internal loopback can't cover the equalization functional test, especially for the CTLE. Actually, we don't know if the CTLE has the right function in the internal loopback. So I want to know, is there any good method to cover it?
Very good question. Yes, this is a major challenge in doing a production test or high volume test of the high-speed links, especially the equalization, the CTLE. Sometimes you may not be able to do it on the unpackaged wafer. Once it is packaged and put on the board, a long loop back can be done on the board, provided you know the loss on the board, and a long loop back test can help whether your adaptation and the coefficients that you selected during design are good enough or not.
Yeah. Okay.
But
you're meaning you
on the wafer level
okay.
CTLE test, I'm not aware of. Usually, it's very difficult to do. It's only the loop back test that you already mentioned.
Yeah. Okay. You're meaning we should use the external loopback to cover
Internal loopback, and if you want, you can have the packaged part placed on the board, and through a board trace, you can do a slightly longer loopback.
Okay. Okay. Thank you.
That can be done.
Okay. Thank you.
Any further questions? Otherwise, I have a question, Tapas.
Sure, Sanjay.
Yeah. So for these high speeds like 112 Gbps and 224 Gbps, right? We do this equalization as you mentioned. So does it take care of the reflection thing altogether, or do we have to do something more vis-a-vis the standard techniques that we have to minimize reflect?
I didn't show it here because I wanted to keep it short in this particular slide. Definitely this termination, you can say.
Yeah.
Their termination is not just a resistance, not just calibrated resistance. They do have inductors, usually bi-coil or T-coil inductor to take care of all kind of capacitive loss and reflections. There are specifications for return loss, which is to take care of the high frequency reflections. Even after that, if you are left with something, usually in DFE, and also you can do it in FFE, but that becomes a little bit more difficult. You can introduce some amount of floating tap in DFE as well as in FFE, where you can kill the reflected waveform. If there is a reflected wave and if you have a floating tap, the tap can move to the reflection point and subtract the reflected amount. So floating tap DFEs are commonly used to take care of reflection to some extent. But if the terminations are bad, you have a bad reflection, no, that cannot be fully taken care of.
I see. Okay. Thank you. So we are at the end of the hour. I think we have email ID from.
Before you close down, I have a question for Tapas.
Yes, please.
So Tapas, thank you so much for giving such a good talk and enlightenment talk. Lot of knowledge in 2 hours. Thanks for preparing and thanks for explaining so nicely. I have a question regarding the PAM4 kind of modulation which we are going through it nowadays. What are the specifications? How tough is the specifications of ADCs there? What kind of ADCs you require?
As I told you some time ago, it's 28 GSPS or 56 GSPS, or for that matter, for 224, 112 GSPS kind of ADC is needed. Usually these ADCs are, you need at least 5 plus ENOP, you can say, effective number of bits. And they are usually asynchronous ADC. I mentioned that one already. And time interleaved, because you cannot have a simple SAR ADC at that speed. Usually they are SAR, they are asynchronous SAR, operating between 1 to 2 GSPS as of today. And you need 56, 64, 128 of them together to put them in a time interleaved fashion, maybe in 2-stage time interleaving. You try to manage them. The spec already mentioned that it has to be 5 or 6 plus effective number of bits. Speed also I mentioned. What else? More or less, these are the kind of parameter that you need.
Okay, thank you.
I believe I tried to pack in as much as possible, remove a lot of stuff to pack things within 2 hours. I believe people followed it, those who are especially the young engineers and students, or I don't know whether people really dropped off in between. I didn't take account of it.
No, I think
it was quite
people are there.
enlightening. Yeah.
In fact, we have the largest attendance here, for this year, I would say. So this is one of the, crowd pulling event, I would say. So thanks to you.
Okay, as long as I could communicate to most of the people, I could make the students interested in this field. As I mentioned that there's a huge demand of this particular technique in the semiconductor industry. And beyond AI and ML, the electronics engineers should be more interested in this kind of hardware. There are a lot of challenge in it, and we do need good brains to work in it.
Yeah, for sure. Thank you once again.
Indeed. Thank you, Rakesh.
Yeah.
And thank you once again, Tapas, for such an enlightening talk. We are quite 5 minutes past the time, and we can close this session. Once again, of thanks. Thank you very much on behalf of IEEE SSCS Daily Chapter. Really appreciate all the presentation making efforts and delivering and all that you have done. Really, really appreciate. Thank you so very much.
I must thank you. I appreciate you called me over here, and it's my pleasure to talk to so many bright brains around.
Yeah.
Thank
you
you
so very much.
Thank you so much.
Thank you.
Have a good
Bye-bye.
day. I sign off.
Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye.